Hello and welcome to Cuda Weekly. I'm your host Johan Bontes, and today I want to talk about double. Floating point double is not my favorite data type because it's big, it's bloated, and it's slow. You may think it's twice as slow, but on a GPU it's much worse than that. Let's talk about it. Here is a throwback to episode 2 where we discussed printing on the GPU. If you look to the right, you'll notice double to single performance 1 divided by 32. So that means that whereas the GPU has a full contingent of single floating point performance, it only got 1/16 of the double performance, and because double takes twice as long as single, you get 32 times slower performance for double. This is for the Tesla T4, but pretty much any GPU you can install on your workstation outside of data centers has the same issue. So the official line is 32 times slower performance. Let's see how this actually works out in real world code. Let me run you through the code. We start with a floating function that takes a single or either double, it's templated. It runs the code 5 times to allow the optimizer's time to stabilize, and we have all our variables to be volatile so that the optimizer doesn't reorganize things, and that makes Cuda timing. We start by taking a clock, and then we have an intermediary C. We do some calculations again 5 times in sequence, and then we take the end time. We print all this stuff at the end to make sure that the optimizer knows that all these values are really used and can't be optimized away. We print the time and the data type. When we look at the time, you can see that single takes about 82 cycles, and then the double takes slightly longer, 600 cycles. It is about 8 times longer. So why is the performance difference only 8 times and not 32 times as advertised? Let me show you the code for the float and the double side by side. So here's the float code. I can copy paste that. Maybe here. And here on top we have the code for the double version. This is the start of the clock for the float. Here's the clock for the double. And if you look at the instructions, they are pretty much the same. Double instructions just have a D in front of them. The float have an F. However, the floating point instructions have a full contingent of execution cores to execute the code, whereas the double do not. So what is happening is the following. When we copy paste these instructions, the scheduler that schedules the instruction that the GPU needs to execute, or rather the warp in this case, schedules 8 instructions in a row for the different sections of that particular core. Now, each core has its own register, so the R4 do not get confused. There are R4s for a different set of cores. And here as well, we have this multiply instruction that gets repeated 8 times in a row so that we get to the total number of double multiplications here. That means that all these instructions that you see here are independent of each other, whereas the floating instructions form a dependency chain. R0 here is the result, and R0 is the input for the next instruction, and the input for the next instruction. So this forms a long dependency chain. The dependency chain for the double instructions is shorter because all these R4s, whereas they look the same, are R4s for different cores, so they're not the same R4. So these are independent, and that means that the dependency chain for the double instructions is broken, which is the reason that it doesn't take 32 times as long, but only 8. Still bad, but not as terrible as imagined. I tried to construct code that shows a bigger difference between float and double in performance, but I wasn't really able to. For some reason, whatever naive code I can come up with always shows these 8 times, sometimes less, sometimes 4, sometimes I got to 2, but I didn't get all the way to 32. So I guess 8 is a pretty reasonable estimate for the real world difference that you get between float and double on the GPU. If you're on a professional GPU like the A100 or expensive systems like that, then of course you have the same number of double execution cores as you have float execution cores, and you won't see this massive difference. In fact, you might not see any difference at all due to how the latency works. On consumer GPUs, we have a difference of, well, about 8, and we have to live with that. So yeah, I guess I'll leave it here. Thank you for watching. If you liked the episode, feel free to give it a thumbs up, and I'll see you next week.